This discussion focuses on PhotonAssay precision at low grades. We discuss the difference between the physics-based method of PhotonAssay and geochemical methods, with the main takeaway highlighting that sample mass is the most important thing when it comes to measuring samples at low grades. So a question we often get asked about is instrument precision at low grades. From your perspective, what do you classify as low grade and why are low grade samples important?
In general terms, a lower grade is probably sort of 0.5 gram a tonne or below. In perhaps some very bulk mine operations where you got low grade, hell, 0.5 might be the ROM grade, particularly if there's copper in there as well. In most gold deposits, the lower grade is probably hitting around the cutoff. So if you think of an open pit operation now, on average, you've probably got a cutoff grade of somewhere between 0.3, 0.5, maybe 0.6, depending.
And why does precision at the cutoff grade matter? I mean, how does that affect things?
We make the decision based on a block, but where we might make a decision based on a sample is actually, earlier in the process when we're actually trying to draw our wireframes. We can get situations where it's all grey rock, but somewhere in there it goes from very, very low grade to something that's mineable back into low grade, and we might struggle with geological criteria and need to fit that wireframe based on a grade value.
And the thing with those low-grade samples, when we talk about precision, we're talking about total precision, so you're talking about sampling error in combination with instrument error. Sure. So it's always interesting because yes, we have a higher instrument error at that point, but PhotonAssay is measuring a much larger mass, which means that we often find, especially when we do studies on these kind of things, when we compare the results of total precision between a crushed PhotonAssay, a pulverized PhotonAssay, and a fire assay result, crushed PhotonAssay is usually very close to the fire assay, with then a pulverized PhotonAssay either producing a similar result or a better result, even at lower grades.
That's a really good point, because I mean, one thing that's very easy to do is to just look at straight instrument performance. So you run your standard CRMs at 0.3, 0.2, 0.1 ppm, you get a pretty direct measure of instrument performance. And yeah, I mean, look at 0.3 ppm PhotonAssay performance at instrument level, a little bit worse than fire assay. As you go down to lower grades, that gap widens out, and that just reflects the rather different detection limits of the two methods. But your point, Naomi, of including the sampling uncertainty in there is key. And we've done a fair number of studies now where we actually look specifically at this question, look at precision via duplicates, and you see that pure instrument crossover point actually happens at much lower grades than you would think. I mean, certainly, our experience down at that sort of 0.1 ppm level, on real world materials, you're typically seeing fairly comparable performance between PhotonAssay and fire assay. And I think sometimes that's a point that gets a little bit lost. It's very easy to look at your control charts on your CRMs. It's more work to kind of go back and look at the performance on duplicates, but it's certainly a good thing, I think, for people to be aware of. I mean, I think another factor that kind of kicks in there as well, and this just really reflects the difference between a chemistry-based technique and a physics-based technique like PhotonAssay. With chemistry, where you're having to go much further on your sample prep, you're having to pulverize, concerns around contamination, crosstalk between samples. I guess you often hear this, you really shouldn't be using data if you're much less than, say, 10 times the detection limit. One of the things that we've been able to show quite nicely with PhotonAssay, because we know where the uncertainty comes from, we actually measure and report the uncertainty sample by sample. We've got a lot more confidence in our data down much closer to the detection limit. I mean, you look at our paper detection limit, 10 ppb, we're still able to offer reasonably confident numbers down to, significantly below 100 ppb or 0.1 ppm. And that, again, may be something that people are just not too familiar with coming from a more traditional fire assay background.
I think when it comes to new technology, you can't just take one in and put new technology in the same spot and just expect everything will all line up. But obviously understanding that, 0.1 ppm is really the limit of what you're working with most of the time.
Yeah, I can't think of any instances that I've had where, if as long as you can get down to 0.1 securely and safely, so to speak, but you'd have too many too many issues?
And we're obviously coming here from a perspective of sort of resource definition, but think about exploration as well. I mean, that's another area again, I guess, one that collectively we have less experience in, but clearly an area where sort of measurement at low grade is important. I mean, to be clear, if somebody's looking at 1 ppb or sub ppb type levels, PhotonAssay is not going to be a method that's applicable. And certainly that's the experience we've seen from, I guess, a large number of studies. I mean, this is an area that we've looked at in quite some explicit detail. PhotonAssay will, on real world materials where you're dealing with all the question marks around sampling and heterogeneity, it hangs in there to a pretty low grade and maybe lower than you'd think about just by, a naive comparison of detection limits for different methods.